Alright, welcome. So here's a short video that talks about how to use this virtual ecosystem that is under development. This code goes through a lot of changes very quickly, but I'm trying to keep somewhat updated on the Git repository and the copy of it that you can download from the EEXIST website. So here's the highlights of this. So if you go to the exist.org status page, which shows you the current status of system that I've got running in the background, if you go down to the bottom, you'll see a link to the Twitter feed, but also to the full directory of code and files. So click on that and you'll see a directory listing. This is all of the source code, all of the class files, documentation, and so on and so forth. To play with the virtual ecosystem, you're going to want two files from here. One is VEco.jar, so click on that. You can tell it to go ahead and download it if it asks whether you want to keep it or discard it. There's nothing in here that should do anything bad to your system other than create a pair of files that will grow slowly over time. So go ahead and keep that, and then main.jar is the other jar file. So download those and go ahead and keep that one, and let's go ahead and open these in the download folder. We can close out our browser at this point. Usual disclaimer here, nothing in this code should do anything harmful to your system. It does open a port which is connected to from the other program that you're going to run, and it creates a pair of files which slowly grow. If you don't exit these programs correctly, they'll keep running in the background, and that can slow down your system. You can always reboot. But there's absolutely nothing malicious in here. So let's go to the download area, and here's how we're going to run this. First thing you're going to do is click on VEco.jar. Just do a single click on that, and it should open a window. It'll show you which port it's going to try to connect on. This should be something unused. And just click Start, and that's going to open your window. And then to actually start running the virtual environment, go ahead and click on main.jar. Again, just click it once, and that'll do two things. It'll open a control panel, and it will also start the virtual ecosystem running. So let me go ahead and make this window a little bigger, and this will, always show you the entire universe. It'll scale the size of the cells. You can go ahead and take off the grid and then click Show Data, and you'll see on each of these organisms an ID in top, such as 36, 42, 9, and an energy below that, 144 in this case, which shows you how much energy the organism has. Darker organisms have less energy, brighter have more. The green dots are food. That's where the organisms get energy from. So these creatures basically move around under their own decision-making process. If they encounter a food dot, they absorb the energy from that. If they hit a wall, they're stuck. The model does not wrap currently. If a creature encounters another creature from the side, it can consume energy from it. If it tries to go forward, it's considered an attack. It takes a certain random amount of energy from the creature being attacked, and it gains that energy itself. If the energy drives down to 0, the creature dies. Each time a creature moves, it expends 1 unit of energy. And that's basically the mechanics of the system. Breeding takes place in one of two ways. If two organisms come face to face with each other and they have sufficient energy and the population is small, and one tries to move into the other, that creates an offspring, and the offspring is a hybrid of the two parents. Energy is randomly populated throughout the universe, and offspring are randomly introduced into the universe as long as the population remains below the population cap. When this breeding takes place, two individuals are chosen at random, but if two or more individuals are considered old, then parent selection occurs only among the old individuals. So this system plays out in that way. A few things we can do with the control panel. So we can tag interesting individuals. So let's say that we find individual 64 to be interesting. We can say tag 34, and now they flash yellow, so it's easy to find them. If we decide we're not interested in them, we can tag them again. If you want to examine what's actually happening inside a organism, for example 45, I can say examine 45, and it brings up this window that if you click anywhere inside this white region, you'll get a detailed view of the chemical balance inside this system's EEXIST. So let me blow this up a little bit. So you can shift scroll to make this wider, and you can scroll to make it taller. This is basically the chemical distribution. These 5 regions represent the inputs, and this region over here from 24 to 28, this is the output request from the system. If you check just the bias, you see the bias gradients. This is basically the genome of the organism. If you check both, that bias gets added. This is the effective source and destination addresses. And this is just the live view of that organism's chemical balance. So that lets us look at creatures. We can clone organisms. I can use the F command and bring up a file listing, and in this case we only have one raw file in this directory. This is raw1.txt. That's the system that's currently running. So I can select that, and now if I do something like examine creature 10, so here's creature 10, and I can look at their genome, and then I can examine 45. So here's creature 45, and I can look at their genome. And they have different genomes, as you can see. I've got some amplification here, but the basic shape is completely different. So I can say, let's clone creature 45 into creature 10, and when I do that, creature 10's genome now matches creature 45's. So you can clone genomes from one creature to another, and that will presumably cause them to run the same algorithms, but that's still an open question. And you can do this on any of the files, any of the raw files that are being saved. So as these programs run, you get a pair of files, raw.txt and out.txt. And they're tagged with a number in the middle. That number will grow sequentially. If I run another one of these systems in the same directory, it'll be called out2 and raw2. So out grows fairly quickly. It shouldn't get much more than gigabytes in a few days, but you might want to keep an eye on it. But the data in here is basically a cycle number. I means it's an individual that's being recorded. This is the ID of the individual, and this is its energy. So it's just tracking energy levels among individuals. This also records breeding operations. So it's cycle 182. Individual 33 had 120 energy. They mated with 35 and created offspring 51. That was the first new offspring. And if we scroll, and 51 gets a shot right away, so it's got energy 76. And if you scroll down, you'll find individual 51 again. They've still got energy 76, and so on. The raw file is the one that contains genomic information, so records can be either S, K, P, or T. S is showing you the basic state of the EEXIST system, and I is showing you information on individuals. So if I want to see, for example, individual 1, this is their full genome right here. And it's basically pairs of numbers, so source and destination bias gradients, so starting points and then slopes. You don't need to know that, but you can go into the code and dig out the details of it. But basically that's what describes the nature of an organism's behavior. So when you examine an organism and you click through and you say show me the bias, that's the genome that's stored in the raw file. Alright, there's also a daily cycle of light and dark that's taking place. Let's go back and look at an organism's chemical distribution. So here's the chemical balance, and remember these first 5 regions are inputs. So this region 4 right here, that's the daylight basically. As the system cycles and gets brighter, this amount of chemical in here increases, and as day turns to night and things get darker, this amount of chemical decreases. So there's the high level, and now it's going to start to come down. Regions 1, 3, and 5 are indicating information about what's to the left, in front of, and to the right of the organism. And region 2 is a wide range radar that tells you if anything is located in the immediate vicinity, but with no particular information. The thing that you can do is you can introduce a drone into the system. So I can use the D command, and it creates a virtual creature that I have control over. So it starts flashing. It's automatically tagged. In this case, it's creature 109 over here. And now in the command window, I can hit single keystrokes, F, L, or R to go forward, left, or right, or Q to quit. Don't hit enter after these. It won't pay attention to it. And don't hold down the F key, for example, because it will not pick up each keystroke. So I'm going to hit F, move forward, eat that energy dot. My energy just went up to 195, and I can move forward, turn right, come down here, and if I go forward, I will attack creature 61. So I take some energy from it, and I can do that a few times and drive its energy down. And if I do that too many times, I'll actually kill it. And I take all of its energy. So this is a way to basically be able to move around and interact with other creatures in the organism. Now, the average organism is not going to be terribly responsive at this point because we're still early in the evolution. But eventually you may find that as you go up and you get close to or attack an organism, it may respond, and it may try to move away, or it may come back and try to attack you, and so on. So these are the kinds of behaviors that we can check for and experiment with by using this drone. When you're done playing with the drone, just hit a Q, and it continues to remain there, but it's inert. It's basically an energy source. So if you don't want to watch it flash, you can detag it. But you can't move it around anymore, and it will do nothing on its own. When you want to exit the whole simulation, it's important to exit the control panel using the Q command. If you just hit the X up here, the Java code will continue to run. So just do an uppercase Q for quit. The control panel will close out. The simulation will stop. At this point, you have two options. You can go back and re-click main.jar, and it will begin a new simulation with new creatures and so on. You can quit that with Q. And then when you want to exit the VEco window itself, you can X that out safely. Each time you run this, you get a new pair of raw and out files. The tag number on these increases automatically. So things to watch out for: keep an eye on the file size, make sure they're not growing too quickly. They should grow pretty slowly compared to the size of a modern disk. The other thing is, if you exit these things improperly, the code may continue to run in the background. So go into your task manager, look for anything with the name Java on it. That's the code that's running, and you can try this once you start the code. Go ahead and look for that in your task manager, and if you don't want it running, you can kill it from there. That's about it. Have fun. Follow the Twitter feed if you want updates. Go to the directory. Feel free to download the code, take it from Git, make changes to it, do experiments, and let me know how things go. All right, thanks for watching. Bye.